Hello, I am Ramani Kruti, roll number 77. Let us see how filtering in frequency domain is done. Generally, the process of filtering involves convolution operation. But when we perform this filtering in frequency domain, this convolution operation simplifies into multiplication. So, for fast and easy computations, we perform filtering operation in frequency domain over spatial domain. Now let us see how padding is done in frequency domain. Firstly, construct a frequency domain filter as the same size of the image. After that, compute the inverse discrete Fourier transform of the frequency domain filter to get a corresponding spatial domain filter. Now pad the spatial domain filter and then convert it back into frequency domain by computing the discrete Fourier transform. Here we can observe that there are four images. The first image is a rectangular function in frequency domain. This rectangular function is converted into spatial domain by computing IDFT. The spatial domain is nothing but a sinc function. This sinc function extends up to infinity. Next, the third image shows the padding effect. The padding of the sinc function results in this image. Padding is done on both sides. After completing the padding operation, we perform DFT and convert this back into frequency domain. So this is the final result obtained after padding in spatial domain and converting back into frequency domain. Here we can observe that these factors extend up to infinity. These spatial domain factors extend up to infinity. So, to reduce the number of factors, we do padding. But after doing padding, it resulted in two discontinuities. These are the two discontinuities. So, padding results in discontinuities in spatial domain. After getting discontinuities, if we perform DFT operation, this resulted in some ringing effect over here. So this ringing effect is caused due to padding. See this spatial truncation. The spatial truncation of the filter resulted in ringing effect in the frequency domain. Now let us see the Matlab code of this to clearly understand these images. Firstly, we take a frequency domain filter, which is a rectangular function. This is the block of code for creating a frequency domain filter, which is a rectangular function. Now, after creating a filter, we convert it into spatial domain by computing the IDFT. To compute the IDFT, we use the following equation. This following equation results in computing the IDFT. Next, the result is plotted. After computing the IDFT, we use FFT shift function so that the central frequency is adjusted. Next, after this, we need to do padding. So we do padding on both sides by including some zeros at both ends. So after padding, we again plot the image to observe the results. Next, after completion of this padding, we need to find the DFT of the new filter obtained after padding. So that this is the equation of the DFT. So after padding, we compute the DFT and convert it back into frequency domain. So finally, we plot the result of the finally obtained frequency domain filter. So here we can see the results. Firstly, we took a rectangular function and computed the inverse discrete Fourier transform of this rectangular function. We can see that this function extends up to infinity. So to truncate this filter, we do padding. See, this padding truncates the filter, but we get two discontinuities over here after truncation. Finally, if we perform the DFT of this spatial domain filter, we can see that there are some discontinuities. So there is some ringing effect. This ringing effect is due to this discontinuities. Generally, when we take infinite number of components, it results in wraparound error. So we do zero padding to avoid this wraparound error. But when we do padding, we can see that clearly there is ringing effect over there. So doing padding is also not considerable. To overcome this limitation, one of the approach is to pad the image and then use the specified frequency domain filter. But this may also result in wraparound error as there is no padding is done in the filter. But doing padding in the image reduces the error and it is mitigated by separation provided by this padding of the image. Now let us look into what actually zero phase shift filters are. Filters that affect real and imaginary parts equally so that there is no effect on the phase angle are called zero phase shift filters. Generally, small changes in this phase angle results in the change in the filtered output. So, zero phase shift filters are mainly used in this image filtering. Now let us see what happens if the phase angle is changed. We consider two cases. In the first case, the phase angle is multiplied by 0.75 and then IDFT is computed. In the second case, the phase angle is multiplied by 0.5 and then IDFT is computed. Let us clearly understand this whole change in phase angle using Matlab. First, let us read an image given in the book. After that, compute the DFT of the image. After computing DFT, we can get the magnitude and phase of the image. So, after computing the phase, we multiply the phase by 0.75 in one case and we multiply the phase by 0.5 in the other case. After changing the phase, let us compute IDFT so that again we can transform it back into its original form. So this is the actual filter, and these phase stim 1 and phase stim 2 are obtained after changing of phase angle. Result 1 is obtained after changing the phase angle by 0.75 and result 2 is obtained after changing the phase angle by 0.5. Now let us plot the three images, the original image and the image whose phase angle is changed by 0.75 and the third image whose phase angle is changed by 0.5. See, this is the original image. And these are the images obtained after reducing the phase angle. Here we can see that the image shape and everything is same, but the intensity values are reduced. See, this is obtained after multiplying the phase angle by 0.75. The intensity is slightly reduced, but when we multiply the phase angle by 0.5, the intensity is very much reduced and the last image is almost unrecognizable. So We observe that by changing this face angle, there is no change in shape of the image, but intensities are changing. And also the third image is almost unrecognizable. So that now we can conclude that the changes in face angles are not accepted. So zero phase shift filters are used so that these the use of these filters with the use of these filters there is no change in phase angle. So mainly zero phase shift filters are used in image processing to avoid the change in phase angles. Thank you.